story begins in Neuromusculopolis, a bustling town located at the neuromuscular junction between the somatic neuron and the skeletal muscle cell. There is constant activity in Neuromusculopolis, between action potentials being transmitted from the somatic motor neuron to the skeletal muscle, neurotransmitters crossing the synapse, and the opening and closing of cation channels. There is never a dull moment, and relaxing does not come naturally. At the edge of town, on the end plate membrane of the postsynaptic skeletal muscle cell, lives acetylcholinesterase, our hero of the story. Hi, my name is acetylcholinesterase. Acetylcholinesterase is a hydrolase enzyme that works non-stop to ensure skeletal muscle cells function properly, in turn contributing to the overall functioning of the body. He is the counterbalance necessary to ensure the muscle cell is able to relax. No one else possesses his superpower. Acetylcholinesterase's superpower is very important. My superpower is to hydrolyze the neurotransmitter acetylcholine, which is left in the synaptic cleft of the neuromuscular junction once the action potential in the presynaptic motor neuron ceases. Acetylcholine's model is go, go, go. Acetylcholinesterase, in contrast, helps the muscle relax after contracting before the next contraction of the muscle cell is required by the body. Without him, what would anyone do? Acetylcholinesterase watches from his home on the end plate membrane, patiently waiting for his time to shine, his time to step in and help the muscle cell relax. I wonder when the next action potential is going to arrive at the presynaptic motor neuron. Wait, I think I see one on the way. Look, here it comes. He watches as an action potential arrives at the axon terminal of the somatic motor neuron, where depolarization causes calcium ions to enter the axon terminal, and the neurotransmitter acetylcholine is released into the synaptic cleft. Like the busiest crosswalk in the world, acetylcholine crosses the synaptic cleft to the acetylcholine receptors on the postsynaptic folds, signaling the opening of the sodium ion channel. This opening allows sodium to flow into the skeletal muscle, causing an end plate potential and further an action potential. Acetylcholinesterase watches as the muscle cell contracts. At the axon terminal of the somatic motor neuron, the action potential ceases, and no more acetylcholine is released. However, acetylcholinesterase notices that the muscle cell is continuing to contract. The muscle cell looks like he's in trouble. If the muscle cell doesn't relax soon, it will start to cramp. The muscle cell is getting worried. I can't stop this contraction on my own. Will acetylcholinesterase please help me before I start to cramp? Will his superhero arrive in time? Luckily, for the muscle cell, acetylcholinesterase is always ready and willing to help. I know exactly how to help the muscle cell. This is my time to step in. I need to break up the acetylcholine left in the synaptic cleft in order to close the sodium channel, which will stop the action potential from being formed in the muscle cell and ultimately stop the contraction. So he grabs his three most important amino acid sidekicks, serine 203, histidine 447, and glutamate 334, which form the catalytic triad of his active site. Hey, serine 203, histidine 447, and glutamate 334, I'm going to need your help on this mission today. Are you three up for it? We sure are. He also calls on his friend Water. Hey, Water, I'm going to need your help today on this mission. Sure thing. You just tell me when I'm needed, and I'm here to help. And together, they get to work. First, acetylcholine enters the active site of acetylcholinesterase, where acetylcholine is captured and held in place by the binding site. I can use my anionic site to form an electrostatic interaction between my oxygen and nitrogen on acetylcholine. This will hold it in place in the active site for the rest of the reaction. In acetylcholinesterase's catalytic site, he gets to work on cleaving the neurotransmitter. Hey, serine 203, do you mind if I borrow your hydrogen atom? Yeah, sure thing. This interaction results in the creation of a nucleophile, serine 203, which can now attack the carbonyl of the acetylcholine. However, now the negative charge on the oxygen is unstable. To stabilize this negative charge, the double bond between this negative oxygen and carbon is reformed. As the double bond reforms, histidine 447 knows that he can protonate the substrate in order to release the first product of the reaction, choline. If I can donate my proton to this substrate, then the choline will break off, and our mission will be halfway done. Histidine 447's actions lead to the cleavage of the first substrate, choline, which is then released from the active site. The first part of acetylcholinesterase's job, to help the relaxation process, is now complete. But for the next step, he'll need to call in a friend to the active site. Hey, Water, I'm going to need your help for the next step. Sounds good, acetylcholinesterase. I'll be on my way to the active site. Water's job is to act as a reactant, and his first job is to interact with histidine 447. Hey, histidine 447, if you take my proton causing me to deprotonate, I can become nucleophilic and attack the substrate. Sounds good, Water. I will take one of your hydrogens. Once water is deprotonated, it attacks the ester functional group on the substrate, which is still attached to serine 203. However, there is once again an unstable negative charge on the oxygen of the substrate. To stabilize this negative charge, the double bond is reformed between oxygen and carbon. And just like the last time, histidine 447 knows that he can protonate the substrate in order to release the last product of this reaction, acetic acid. And the mission is complete. If I can once again donate my proton to this substrate, then the acetic acid will break off and our mission will be complete. Histidine 447's actions once again lead to the cleavage of the final substrate, acetic acid, which is then released from the active site, completing the mission. We did it! Together we were able to cleave acetylcholine into choline and acetic acid. Acetylcholinesterase did it, and with the help of water, together they hydrolyzed acetylcholine into choline and acetic acid. Another step in the relaxation project. But our job is not done yet. We need to repeat this process until all the acetylcholine is gone from the synaptic cleft. Acetylcholinesterase does this over and over again until there is no acetylcholine left in the synaptic cleft. When they finally finish cleaving the acetylcholine, the muscle cell, to his delight, relaxes. And he is so happy acetylcholinesterase was able to help him. Thank you so much, acetylcholinesterase and friends. I couldn't have relaxed without your help. I would have been stuck contracting forever, and eventually would have cramped. You are the true hero of Neuromusculopolis. And that is the story of how acetylcholinesterase helps the muscle cell to relax. As we leave Neuromusculopolis, if you look closely at the end plate membrane of the postsynaptic fold, you'll see acetylcholinesterase, our hero, waiting to help out the muscle cell once again. I am always ready to save the day and help the muscle cell relax.